Welcome back my dear students. A very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And as you know, this is the DADM 3, which is Data Analysis and Decision Making 3 course under the NPTEL MOOC series. And this total course duration is basically for 12 weeks. The total contact hours is 30 hours, which when split into the number of lectures is 16 number. And each week we have basically 5 lectures, and after the end of these 5 lectures you have one assignment. So, as you can see from the slide, which is the 7th week. So, after this you will basically be taking the 7th assignment, and after the end of the 12 different assignments you will be taking the final examination. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember, we were discussing about the concept of loss functions. Loss functions in the sense that provided that you want to estimate the parameter using the sample statistic, which is theta hat. So, theta hat minus theta, if it is considered as a quadratic loss function, it is something to do with the utility functions also. So, I am not going to go into that detail. So, if it is a quadratic loss function, then trying to find out the minimum of that loss function also is akin trying to basically find out the minimum variance, which basically makes very good sense in the statistical concept. But other type of loss function which are utilized in statistics and other studies is basically the mod function, where the both for the estimation on the right hand side and the left hand side, which is overestimation underestimation, is equiparallelized, but it is straight line in the sense you are taking the modulus of theta hat minus theta both on the right hand side and the left hand side. So, the only problem which I mentioned is that at the point of 0, which would be considered the point where trying to find out the dy dx of the function would be difficult. Now, if I consider the nonlinear loss function, considering the fact that if it is a modular loss function. So, I mentioned that just when we wrapped up the 34th class, I said that I will go through the diagrams accordingly and then come into the practical applications of some of the actual realistic loss functions which we generally utilize. So, in the first instant we consider that the value of k 1 is greater than k, hence the overall loss which is there, if k 1 is greater, then obviously the overall loss which is or the gain, let us put it in a way that if you are looking at the right hand side, but generally there would be loss, but because there is a difference between the estimated value and the actual value. So, the overall loss function which is there on the right hand side, when theta hat is in minus theta or delta is positive, it will be more penalized on the right hand side and less penalized on the left hand side. The moment you basically consider the values of k 1 k 2 are swapped, then as it is shown in this slide, underestimation overall loss would be much more penalized than the overestimation, hence the slope of the red line is much sharper than the blue line. Now, again obviously the problem remains trying to basically find out the dy dx of this function at the point of 0 is impossible, hence even though it looks interesting, we would not be utilizing that for our practical purposes. Now, in the 1970s, 80s and 60s, work was basically done by Hall Varian, who is basically in the area of economics, in order to basically predict the prices of houses or trying to basically study the overall effect, that whether overestimation and underestimation can be broken down in such a way that they would basically make some practical sense. Now, this was basically initially from the economics point of view. Later on, Arnold Zellner took this up as a statistical study, where he proposed the statistical properties of a loss function which is known as the linear exponential loss function or the Linux loss function. The Linux loss function basically looks like this, the diagram. So, I will come to the diagram why this diagram looks like this, but first let us basically concentrate on the equation. So, basically there are two parts. The first part is the exponential function, which I will now try to highlight using a different color. So, this would be the exponential part, and if I am considering the linear part, it will be this. So, now see the beauty of the loss function, and obviously b and a are some parameter values. So, if b, if it is multiplied, it basically scales up or scales down the overall loss function which you have. Now consider the theta hat minus theta is positive and A is also positive. So, in that case what will happen, that if you consider any value on to the right, that is delta is positive, that is theta hat minus theta is positive, then the exponential part will start increasing exponentially as you go and as you increase the values of delta. But it will happen in such a way that there is obviously a negative part. Negative part is what? Is basically minus A in the bracket theta hat minus theta, but the rate of increase of the exponential part would be so high that it will basically dominate the linear part. Hence, the right hand side of the equation, which is in the first quadrant, would be basically increasing exponentially, while if I consider the left hand side of the equation, left hand side of the diagram, which is there onto the second quadrant, in that case obviously A is positive, which is fine, but the value of theta hat minus theta is now negative. So, if it is negative, so obviously you have an exponential function with some negative value. So, as it start increasing, the left hand side is increasing, if you go more and more onto the left, then in that case it will be 1 by that exponential function, which will basically decrease exponentially. Hence, it will mean that the linear part would slowly start dominating the exponential part. So, hence the left hand side, even though the diagram may not be drawn very perfectly, the left hand side would basically almost be a linear function, while as I mentioned earlier, the right hand side would be an exponential function, because in the right hand side exponential part will dominate the linear part, while in the left hand side the linear part would basically dominate the exponential function. Now, consider the fact that I basically reverse the A value. So, I take it negative. So, in the case when I take a negative, when I go into the right hand side, which is the value of delta greater than 0 or theta hat minus theta is greater than 0. So, in that case the exponential part which is already there, it would now become 1 by e to the power some value, because that negative value would bring it to the denominator, while the positive part would be, the linear part would be with a minus A, it will become positive. So, any values which is linears would basically start dominating the exponential part. So, the right hand side of the equation would basically look exactly what we have seen in the previous diagram. So, that will be linear in nature, while if I go to the left hand side, the left hand side would basically would be such that it will be with a minus sign if I am considering, and also theta hat minus theta is also minus. So, in that case exponential would be a positive value, hence the dominance of the exponential part would be so large than the linear parts. Hence, in the second quadrant you will basically have a exponential dominated curve, while in the right hand side in the first quadrant you will basically a linear dominated curve. So, the linear exponential loss function would basically be more penalized when the value of theta or when the value of A is positive and you are concentrating on the right hand side, which is the first quadrant, and it will be penalized more on to the left in the second quadrant if basically A value is negative. Now, the interesting part of this equation is that if I basically zoom in and around the value of 0. So, if I basically zoom in here, so if I zoom in here, then the graph would look like this. So, yeah, I use a microscope, zoom in. So, it will be almost a quadratic function, very near to the value 0. So, I am not considering any higher values, and this will be true from the equational perspective also. Why? Let me write it down. So, consider the exponential loss function. So, you will basically have e to the power some A delta. So, let us expand it. The first term would be 1, then the next term would be basically A delta by 1 factorial. The next function would be A square delta square by 2 factorial. I am expanding the A part, and then the cubic part to the power part I will continue. So, let me put it at dot dot dot. Now, if I consider 1 and 1 here, they will cancel out, because that other one is basically negative. So, basically this value and this value cancels. The value of A delta by 1 or A delta basically cancels. So, these are plus and minus sign as it is there, and this exponential I have already expanded. So, if I consider the third power as quadratic and higher powers to be neglected, considering that they are delta cube, which will basically tend towards 0 as we increase the value of a as well as the value of delta. So, the only equation form which will be true for the linear exponential form in and around the value of origin would basically be the quadratic equation, or the if you consider the utility function which you have already done based on a quadratic utility function, which basically gives us the information that the returns of the decisions are normal in nature. So, this is a very typical property of the linear exponential loss function as proposed by Varian and Zellner. So, let us consider two examples here. So, these examples will make the concept of loss functions clear and why it is positive, why it is negative. Consider that you have a product or a company to launch a product, and I will start with the very general example and then come to the specific. So, the company wants to launch a product, and for the launching a product is basically wants to find out that what should be the actual price of that product, and it gets some information from its competitors from the market, and then it launches the product. So, considering the price of the product is, say for example, 100, and I am basically trying to sell it in the market at the value of 90, right. So, in that case what will happen that, and also I consider that depending on the price I give a high or a low warranty life. So, in this case what will happen is that I am not specifying whether I give a high warranty life or a lower warranty life. So, in the moment basically I go for a lower price, people will be tempted to buy my product, but the fact would be a higher or a lower warranty life would mean that if a higher warranty life is there, actually when it is not required, it will mean the products will start failing much before the warranty life which has been given by me. So, in that case I will basically be incurring a huge amount of loss. In the other case, if I given a warranty life which is less actually as it should be, and still the people buy, then in that case my warranty life would not be violated and I can increase my sales accordingly, because by the word of mouth my current product will be considered as good. Now, in this case whether the warranty life should be higher or whether the warranty life should be lower, or whether the price is higher on an average or lower on the average would basically depend on other data points or other information which is available with me. So, let me read the problem. Considering company plans to launch a new product, say a refrigerator in the consumer market. Also suppose the similar products from different manufacturers already exist in the market. Then the company is expected to give some warranty for that particular product. Warranty means guarantee, that is the refrigerator to his customer. So, they want to give some warranty such that to the customer they would be interested to buy the product, or the company would be able to sell the product provided the warranty life or the guarantee life actually makes some positive sense to the customer. Now, if all the value of this warranty is more than the average time of failure for the product as I just mentioned, then the mentioned company needs to replace the damaged product. So, that means they would definitely be not able to cover the warranty time, replace the damaged product itself, or face litigation problems. In the case that if I do not replace the products, obviously the customers will file a litigation charges. So, in that case I have to basically find out that balancing the fact that if I give a warranty life is lower, whether I should replace the product or basically face the litigation charges, whichever is high we will take the decision accordingly, so that we do not face a huge amount of loss. On the other hand, if the warranty period is less than the average failure time of a similar product. So, basically the warranty now overall value is switched, then the average failure time of a similar product available in the market, then the company loses the market shares to its rival, because the warranty life is higher, then obviously people will be if it is lower, sorry, your product is lower, people will be attracted to the rival product. Under such a situation, it is definitely advisable to estimate the warranty life time period using an asymmetric loss function. What values of A should be, so if it is whether it is positive or negative, should use. So, when you are trying to utilize A, you should use the concept that depending on the level of importance you want to face for overestimation and underestimation, you will basically put the value of A as positive or negative. So, overestimation means that you want to penalize much higher on the right hand side, and underestimation means you want to basically penalize the underestimation part much higher. So, what values of A one should use would then depend on the level of importance our company or your company places on the overestimation problem versus the underestimation problem, that is the cost of litigation versus the cost of loss in the market share. So, in case if I am losing the market share and also basically losing the litigation, then it is a disaster for me, but in the case when the market share is increasing, but even that I am able to offset the cost, then obviously it will mean that I do make some sense when I am trying to give a warranty life which is higher or lower than the ordinary average value which I want that to be. Consider a second example and consider an civil engineer. He is trying to build a dam. Now, assume that the dam height is 120 feet, but there are two instances. Consider in the first instance the engineer builds a height of the dam to say for example 122 feet with respect to 120. And in the second case the engineer builds the height to 118 feet with respect to 120 feet. So, in both the cases the difference would be 122 minus 120 which is 2, whole square of that is 4, and in the other case it will be 118 minus 120 whole square of that is 4. So, if I am basically trying to plot it on a quadratic utility function or quadratic loss, so both the values of positive and negative would be equally penalized if I go on to the right hand side or the left hand side of the estimated difference of the estimated value and the real value which I try to find out, or the parameter value which I try to find out as delta and plot it along the x axis. Now, what happens in the case if it is built to a height of 120 feet, the initial cost is much higher. So, this man hour cost, material cost, so on and so forth. But when say for example, the flood comes, the propensity of the flood to breach the dam which is of height 122 feet with respect to 120 feet is much lower. So, hence we do not face any catastrophic loss. But on the other hand, if the height is 118 feet and if a flood comes, then the propensity of the flood to breach the dam is much higher. So, initially we may not have spent that much of money to build in comparison to 122 feet. We have not used that money because we did not use materials, we did not use labor costs. So, we have been able to save that our total amount of money, but in case as I said, if the flood comes, the propensity of breaching the dam height which is 118 feet is much higher, then in that case the overall catastrophic loss is much higher. So, in the first instance when you have overestimated it and in the case when you underestimated it, the overall losses in the underestimation case would be much higher. So, you will be tempted to utilize or practically it is useful to utilize a value of A which is 0, such that you will penalize the underestimation much higher than the overestimation case. Now, consider the case you have an electrical huge equipment and there are this circuit breakers. Circuit breakers are basically type of switches which are there, trip switches. Now, consider the warranty life of that machine based on the fact that you will basically stop that machine and change these circuit breakers is say for example 6 months. So, if you do not do that, there is a chance that there may be a catastrophic accident. Now, in case say for example, you give an estimated life for that warranty life in one case as 8 months and in another case as 4 months, in both the cases it is 8 minus 6 which is 2 whole square is 4, in the other case it is 4 minus 6 is minus 2 whole square is 4. So, we are happy that both overestimation and underestimation are equally penalized. You will use the quadratic loss function, solve our problem and proceed accordingly. But does that solve our the problem in the practical sense? Now, let us see it. In case if I have overestimated it and I say that it is overestimated in the value of plus 2, then we will be tempted to basically stop this machine in a sense. Overestimated means that in this, if it is 6 and we have overestimated to 8, and in that case we will basically be tempted to start the machine in a sense that for negative values or positive values we will be stopping the machine at a higher level based on 6 or a lower level based on 6 months. So, stopping the machine at a level when the actual time period of change of the circuit breakers has not come, it will only mean that there is stoppages of worker man hours, there is a stoppage of production, but we will be changing the circuit breakers much more often. And in the other case, when basically we underestimate it and then we and we have not been, and we will basically be giving a guarantee life in such a way that we will be basically not changing the machines or not changing the circuit breakers at the optimum point of time. Obviously, the production will increase, but the flip side is that the chances of catastrophic loss is much higher, and in this case we will be tempted to find out the value of the overestimation is more important for us. So, we will basically take a value of A as 0, which means that if you overestimate, then we will basically stop the machine later on. So, the initial cost of production is very positive to us in the sense that we are making more and more profit, but in case if a catastrophic loss happens, because as we will stop the machine later on, hence the overall loss or overestimation will be much higher. But in the other case, when we do the underestimation, we will be tempted and we will be forced to stop the machine much before the 6 months, change it. So, obviously, there would be some losses on the production front, but there would not be any much catastrophic loss for human life or overall accident which may can happen, because we are trying to stop the machine much beforehand. There is another loss function which is used very interestingly in the area of statistics or in area of regression or in area of forecasting, is basically known as the balanced loss function. So, balanced loss function is also utilized, has been predicted or given by the work of Zellner in the 1994. So, balanced loss function works in this way. Say for example, you are doing a regression model, and in regression model our idea is basically to find out the errors. Errors is basically the difference between the actual value, which is y, and the predicted value, which is y hat, and we find out the difference of these errors. And as per the concept of the quadratic loss function which we considered in initial part when we were discussing, we basically try to square this overall loss, add up all the losses for all the estimates which are there, estimated and the forecasted value and the actual value. We add up these square of these losses and try to basically minimize these losses. So, in the case when you are trying to minimize the losses, you will basically try to differentiate these losses with respect to all the parameters which are unknown to us, put it to 0, find out this parameter values using their estimated value, which is hat value, and then our life is done. But Zellner proposed a very interesting loss function which I just mentioned, which is the balanced loss function, where you take there is errors both on two accounts. Point 1, the error is there for the estimation problem as such, that is the parameter values which you find out, that is the values which I just mentioned, alpha hat, alpha 1 hat, alpha 2 hat, alpha 3 hat, which are the concept of the regression coefficient which we have. Now, that would be one error. Another error would be once you use those estimated values to find out the value of the forecasted value of y. So, obviously, there would be a error when we try to find out the difference between y and y hat. Now, what Zellner proposes is basically you try to basically penalize both the concept of estimation error when you are trying to find out theta with theta hat, and also the forecasting error when you are trying to find out y by y hat by utilizing the concept of quadratic loss function, and it can be shown that the properties would be such that overestimation and underestimation can also be considered in unequal proportions in order to come up with some practical good examples. So, the balanced loss function is given as such, where W is some Another thing which I forgot to mention is that when you are trying to basically find out the overall errors. So, there are two parts. One error is basically the estimation error, where as I mentioned you try to basically find out theta using theta hat, and the other error would basically be the difference between the y value and its forecasted value, which is y minus y hat. So, when you are considering some W value which is or lambda value, it is the overall weight we are going to give to the forecasting error and as well as the estimation error. So, if I multiply W or delta with the concept of the forecasting error, so here which I will basically mark is yellow, and the other one when I am trying to basically utilize the estimation error. So, here it will be 1 minus delta 1 minus W. So, in case W is 1, then the overall effect of the loss would all be subsumed under the forecasting error. In case if W is 0, the overall loss would basically be subsumed under the estimation error. So, with W having a given value such that it is 0 and 1, Zellner found out this concept of loss, where it can be split into two parts. One is the goodness of fit, which is the lack of biasness, and one is the precision estimation. So, the precision estimation would be the concept of the estimation which you are doing, which is on the right hand side, which is green in color, and the goodness of fit would be on the left hand side, where you want to find out the difference between the actual value and the forecasted value. The first term represents the goodness of fit, as I just mentioned, while the second represents the precision estimation, which is also termed as the accuracy of the prediction or the forecasting which you want to do. Because based on the estimation on the forecasting niceties, we will try to basically utilize that to do the further forecasting and trying to basically utilize the values of y hat in order to predict the values of y actually which is needed. Now, before I start the DEA concept, I will basically give you a very brief introduction, even though it would not be possible for me to consider everything in this 31st lecture, but I will just give you a brief introduction, and I will start from the slides again later on when we start of the next lecture, which would be on the starting of the 8th week. Now, when we are considering the concept of the estimation problem, as I mentioned, and when we are considering the DEA basically means the concept of data envelopment analysis, where the main focus of the problem is try to find out the efficiency. Now, we are not changing the track, I am basically trying to analyze the problem from the point of view of operation research. Now, given any factory which we will consider as the decision making unit, we will consider there is some bundle of inputs and that some bundle of outputs are produced. So, consider that you have a hospital. In the case when you have hospital, the number of inputs or the type of inputs can be the type of surgery you can perform, the number of type of doctors you have, how good or bad they are, the number of beds, number of nurses, proximity to the say for example, localities where people are there, and output would be how successful the operations are, what is the total number of operations or output the particular hospital is able to perform, what is the recuperative percentage of people who are admitted, or what are the critical cases of health checkups which the hospital does. So, some of these variables or some of the factors would be objective and some of the factors would be subjective. So, trying to basically combine the subjective and objective part would be the main focus when we are doing the DA studies. Consider the next example, say for example, you have a school or a college or an institute and you want to basically rank this institute depending on different criteria. So, what could be the inputs? Key inputs can be the type of students who are going to come, the type of faculty members, type of infrastructure, the library, the curricular activities and so on and so forth. It can be the staff members, proximity to the city where all the people who are from different strata of the society can basically study there. What would be the output? Output could be, say for example, the how many students have really secured very high marks in either class 10 or class 12, or it can be, say for example, how many students have been admitted in different type of professional degrees, or it can be, say for example, how many students have basically excelled in sports. So, all these input outputs bundles will be considered in such a way that you will be able to rank the DMUs depending on some concept of efficiency. I am going to come to the concept of efficiency very fast. Now, another example can be, say for example, we are considering government institute, and the government institute or the government, and we are considering that the government has different type of schemes to perform. See, it can be midday schemes, it can be the performance of the government in trying to basically maintain crime in the city or in the state. It can be what number of such public schools are there, number of public utilities which are there, what are the road conditions, and all these things can be there. So, the input can be say for example, number of amount of money which is being put, number of type of engineers, the efficiency of say for example, engineering department, and output can be successful midday meal, successful number of roads which are in good conditions, the electricity supply connections and so on and so forth can be considered. So, in all these problems we will see that the overall input and output can be classified into some subjective and objective part, such that combining them would give you some scores, and we will try to solve this problem using the simple optimization problem, where we will see linear programming will be heavily utilized. With this, I will close this lecture and have a nice day, and thank you very much.